So we've got our equation of state, otherwise known as the ideal gas law, and then we've got an expression for the total internal energy in our ideal gas with L degrees of freedom. All right, and now we're going to be looking at 4 different processes that our ideal gas could be asked to undergo. All right? And we're going to want to determine the heat capacity associated with some of these. What is a heat capacity? The heat capacity is the amount of heat that's required per change in temperature. So we could say heat divided by the change in temperature. We're going to use the symbol C for heat capacity. You learned in chemistry about something related to the heat capacity. So, as it stands, heat capacity scales with the volume. Okay? It is an extensive quantity. So I can't say, for example, what's the heat capacity of iron, because it depends on how much iron you have. All right? So for that reason, we might want a quantity that depends only on the substance. And one way that we can do that is by dividing this extensive quantity by another extensive quantity. The choice that's often made is the mass. When you take an extensive quantity and you divide by the mass, you get the specific quantity. So the specific heat or the specific heat capacity is the heat capacity per unit mass. And that's given a lowercase c. All right, so I just wanted to point those out before we start looking at our processes. Our first process is, oh, I forgot, I need to also write down our equation for conservation of energy, our first law of thermodynamics. The change in internal energy is equal to the heat energy added to the substance minus the work that the substance does. Okay? All right, so let's look at our processes. An isobaric process is a process that takes place at constant pressure. Okay? We know that the work done by a gas is equal to the pressure times the change in volume. Since the pressure in an isobaric process is constant, we can just use that expression. Pressure times the change in volume. Okay? Now, we know that the change in internal energy is equal to L over 2, pressure's constant, so it's P delta V. That's equal to the heat minus the work. So that means that the heat absorbed in an isobaric expansion is equal to L over 2 plus 1 pressure times the change in volume. Now, the pressure times the change in volume for an isobaric process with a constant number of molecules, so closed system where the molecules can't come in and go out, is equal to N.K. Boltzmann change in temperature. All right, so that gives us a useful expression for the heat capacity at constant pressure. It's equal to L over 2 plus 1 N.K. Boltzmann. All right, so those are considerations taken in an isobaric process. What about an isochoric process? All right, this is a process that's also sometimes called isovolumetric, but isochoric sounds better. An isochoric process is a process that takes place at constant volume. Since the volume is constant, there's no displacement. That means there can be no work done. The work is equal to 0. Okay? So for that reason, the change in internal energy is ascribed only to the heat. Okay? Only to the heat. This gives us immediate access to the heat capacity at constant volume. Because the change in internal energy is just L over 2 N.K. Boltzmann change in temperature. Okay? So the heat capacity at constant volume is equal to L over 2 N.K. Boltzmann. So that means the heat capacity at constant volume gives us direct access to the number of degrees of freedom the molecules of an ideal gas have. All right? Now, the reason why the heat capacity at constant volume is smaller than the heat capacity at constant pressure is because in order to heat up a gas at constant pressure, we need to provide all the energy required not only to increase the internal energy, but also to allow the gas to do the work that it has to do in order to expand. Adding heat, increasing the internal energy at constant pressure requires the volume to increase. But if I do it at constant volume, there's a constant volume. There's no work to be done. So all the heat goes directly into internal energy. So that's one way that we can understand why the heat capacity at constant pressure is greater than that at constant volume. Okay? All right, the next process we're going to look at is an isothermal process. I always want to say isothermic, and maybe I should change over to saying that. But usually I've heard processes referred to as isothermal instead of isothermic. So we'll see. All right? I never think to look it up when I'm not in the middle of explaining it to people. So anyway, all right. An isothermal process is a process that takes place at constant temperature. All right? Since it takes place at constant temperature, it doesn't make any sense to ask about the heat capacity. The heat capacity is the heat required per Kelvin increase in temperature. If I'm not changing the temperature, then it doesn't even make any sense to ask that question. I mean, you could also say, oh, the definition would have us divide by 0. But that's the math definition. If we just look at the English definition, it doesn't even make any sense to ask the question, what would the heat capacity at constant temperature be? The temperature is constant. All right? But we can ask about the work that's done. I can't use this expression, P delta V, for a finite change in volume. And that's because if the pressure is held constant, well then any changes in the volume must also change the pressure. So I have to only use this expression for infinitesimal changes in the volume. Okay? So I could say the work in an isothermal expansion is equal to the integral of the pressure times the change in volume. Okay? As we've seen, work does not represent a change in a state variable. So this integral is dependent on the path that is taken between the initial and final states. If we do it at constant temperature, then we'll have the pressure as equal to N K Boltzmann temperature divided by the volume. So this gives us a very interesting appearance of the natural logarithm in thermodynamics. All right, so the work done in an isothermal expansion is given by N K Boltzmann T times the natural log of the ratio between the initial and final volumes. Okay? Now, we can also recognize that in an isothermal expansion, the temperature stays constant, so that means that the internal energy stays constant. Delta U is equal to 0. So the heat that is input during an isothermal expansion is all changed into useful work. In this sense, an isothermal expansion is a 100% efficient process. All of the heat absorbed by the gas is turned into useful work. All right? And that's a very useful thing to recognize when we're trying to create a heat engine which transforms heat energy into useful work. Okay? An isothermal process will do that at a 100% efficient rate. Unfortunately, I can't make a heat engine just with isothermal processes. Oh well. You gotta live in the real world. That is the way that it is. So I've got to tie together an isothermal process with another process in order to make a heat engine. Now, isochoric processes are not useful in that regard because they don't do any work. And isobaric processes require heat for doing work, and they're not terribly efficient. So the other process that we're going to want to use to make the best theoretically possible heat engine is a process that doesn't require any heat at all. Okay? Such a process is called an adiabatic process. And that will be our last process. Adiabatic, or to give it a name that falls in line with the other names, we can call it isentropic, a process that takes place at constant entropy. Now, we don't know what entropy is yet, so I'm not going to view it from that perspective right now. Instead, I'm just going to focus on it being a process with no heat. No heat flow. Okay? So in this case, once again, it doesn't make any sense to ask for the heat capacity. How much heat do you need at no heat. I mean, no heat. It doesn't even make any sense to ask. Like, why would you even define that quantity? There's no heat. Okay? That said, since the heat is zero, we can look at the change in internal energy. And what we see is that the change in internal energy is just equal to minus the work. So if I was to imagine a gas expanding adiabatically, all right, and you can think of that, it is no heat, but you can think about a process that takes place adiabatically as a process that takes place quickly. In order to absorb heat, a gas requires time. So one very simple way to envision an adiabatic process is to imagine a process that takes place very quickly. One example associated with adiabatic changes is the propagation of sound through a gas. The propagation of sound through a gas requires adiabatic changes. All right? So it's a no heat process associated with vibrations in the propagation of sound. All right, and we'll find that a quantity associated with adiabatic changes appears in the formula for the speed of sound in an ideal gas. All right? So another thing that we can look at that's like a standard adiabatic process is when I have a gas trapped at a very, very high pressure and I open up a small hole in the container that it's stored in. The gas will flow very quickly out of that hole, expanding too quickly to absorb any heat. In doing so, it's expanding, it's going to be doing work, but it's not able to absorb any heat to account for that work. So the work that it's doing comes at the cost of it decreasing its internal energy. Okay? So its temperature will decrease very quickly. And this temperature decrease is not like what happens in a refrigerator, where I just have to pump the heat out. All right? It's not what happens in an ice box, where I have to make sure that I have something colder than what I want the temperature of the thing that I put in there to be. This is a purely thermodynamic process. It's expanding, it's doing work without being provided any heat energy. So its temperature will just go down. All right? And this presents one method that we can use to liquefy gases like nitrogen or helium. We can use an adiabatic cooling process in which the gas cools to a temperature lower than its liquefaction point. Okay? And so that's very nice because I don't have refrigerators that keep things as cold as liquid nitrogen. All right? So I can create this liquid nitrogen using an adiabatic process and then store it in a dewar that won't allow heat from the outside to increase its temperature in any efficient way. So it will keep this nitrogen liquid for a while. All right, so what is the relationship between pressure and volume in an adiabatic process? We know, obviously, in an isobaric or isochoric process, we know what's happening to the pressure and volume. In an isothermal process, PV is constant. So what about adiabatic? Well, this equation is going to give us that relationship essentially for free. So we'll say the change in energy is L over 2 and then d PV. That's equal to minus the work. All right? So if I take the differential on the left and I expand it, I'll get that. And now, if I divide by L over 2, PV, I'll get just like that. Now, this quantity is something that we've already seen. It's the ratio of the heat capacity at constant pressure to the heat capacity at constant volume. Or you could use lowercase, because I could just divide by the mass in the numerator and the denominator and get specific heats instead. So this is the so-called ratio of specific heats, which is given the symbol gamma, not to be confused with the Euler-Mascheroni constant. All right? So in terms of gamma, now I can integrate this equation and find that an adiabatic process is a process in which PV to the gamma is constant. Gamma, of course, is equal to one plus 2 over L, or L plus 2 over L. It's greater than 1. So that means that if we were to compare in a PV diagram an isothermal process to an adiabatic process, isothermal has PV equals constant, or P equals constant divided by V. So that would be my isotherm. My adiabat is going to be P equals constant divided by a power of V greater than 1. So an adiabatic process will work like that. All right? If you were to compare isotherms at different temperatures, what you'll see is that the adiabatic curves decrease the temperature by going down at a steeper rate into curves associated with smaller and smaller temperatures. Okay? And now we can also look at this formula for the speed of sound. The speed of sound, which is also usually given the symbol C, where C is celerity there. There's too many C's on the board, so I'll go ahead and use a lowercase. No, I'm just going to write it in words. That's what I'm going to do. Speed of sound in an ideal gas, I'll write it up here. Is equal to the square root of gamma RT divided by the molar mass of the ideal gas. All right, and we can see here the appearance of the ratio of specific heats, and that's because the vibrations associated with transmitting sound should be treated as adiabatic in nature. They happen too quickly to allow for the absorption of heat. All right, so those are the processes, those are some of the processes, the important ones, that we can have an ideal gas undertake. As I said before, we can make the most efficient heat engine by employing isothermal processes and this other process, adiabatic. So isothermal processes are processes in which all of the heat energy is turned into useful work. So they're like 100% efficient. Adiabatic processes are processes that don't require any heat. So the heat is zero. So it like doesn't hurt. Okay? A cycle that involves only isothermal and adiabatic processes is called a Carnot cycle. Carnot engine. All right? And it consists of, let's do it like this. A process where we have an ideal gas expanding isothermally as it takes heat in. Okay? Then it expands adiabatically, all right, down to a colder temperature. Then it cools. Heat comes out. I said it cools. This process takes place at constant temperature. So it's not actually cooling. It's just depositing heat energy out as I decrease its volume at constant temperature. Okay? There, it's depositing heat out. Remember, at constant temperature, heat equals the work. All right? So what's happening is I'm doing work on it, decreasing its volume. All right? And so the energy that I add into it is sort of deposited out in the form of heat out. And then it comes back up the adiabat. All right, the efficiency in a Carnot cycle is equal to 1 minus the ratio of the temperatures. T cold divided by T hot. And this Carnot cycle is the most efficient possible that we can get for an engine operating between those two temperature extremes.